Every year, between 250 and 500,000 people experience a spinal cord injury. The WHO recognizes that access to high-quality rehabilitation to maximize functioning, independence, overall well-being, and community reintegration is among the primary goals to improve care for people with spinal cord injury. Best practices for rehabilitation therapy recommend standing and walking for 30 minutes per day after SCI, but traditional manual gait therapy is physically demanding for therapists. Robotic gait therapy greatly reduces this burden and is a promising solution for offering high doses of gait therapy for SCI patients. ABLE Human Motion has created the ABLE Exoskeleton, an innovative bilateral lower limb robotic exoskeleton that is more lightweight, user-friendly, and accessible due to a lower price point than other devices. In this project, we've added several innovative features to the device, including a haptic feedback vibration band for the user, pre-gait exercises to enhance motor learning, and gamification in a mobile app. No other devices on the market offer this type of user feedback to assist with learning to use the device. The development of these features make the ABLE Exoskeleton a more diverse tool for rehabilitation, allowing therapists to better utilize this technology and improving the patient experience. After developing the features through iterative prototyping and co-creation activities with the researchers at the St. Martin's Clinic, the prototype device was delivered to the hospital to undergo a clinical investigation. Recruited patients performed 6 sessions each with the device, 5 training sessions, and 1 evaluation session.
We conducted a clinical study at the St. Martin's Clinic in the Netherlands to investigate the effect of verbal tactile feedback on exoskeleton use in people with complete spinal cord injury. The first 5 sessions focused on training, with the aim to enable participants to use the exoskeleton safely and independently. The training sessions alternated between incorporating and excluding verbal tactile feedback. This allowed us to compare performance improvements between sessions with feedback and without feedback. The last session served as an evaluation. We used this session to evaluate the effect of verbal tactile feedback on the overall performance of people with complete spinal cord injury walking in the exoskeleton. During this session, we varied the presence or absence of verbal tactile feedback under different sensory conditions. The results of the clinical study revealed a varied effect of verbal tactile feedback on the learning process and the overall performance of people with complete spinal cord injury walking in the exoskeleton. Among the participants, 2 individuals demonstrated benefits from the feedback, while 1 participant seemed to experience some disadvantages. For the other 2 participants, the results were inconclusive, as no clear pattern could be observed. After the exoskeleton sessions, we collected feedback from the participants regarding the verbal tactile feedback system. 3 out of 5 participants reported that the verbal tactile feedback helped them during the sessions. However, 2 out of 5 participants reported that the feedback was sometimes a bit distracting. In terms of suggestions, the participants provided valuable input. First, they recommended to implement an option in the remote controller to turn the feedback system on or off. Second, they suggested to make it possible to adjust the intensity of the vibrations, as some participants found the intensity of the vibrations a bit too high.
We've created the first robotic exoskeleton to incorporate haptic vibration feedback for use in pre-gait exercises and gamification, which will improve the treatment of people with spinal cord injury. Based on the acquired clinical data and user feedback, we're now ready to finalize the exoskeleton's design and start commercialization.